All right, in this question, the football is kicked at an angle with an initial velocity, and they're asking us three questions. In the first one, they want to know what's the maximum height reached. And you can see that the maximum height, I indicated it here, the maximum height is reached when when the ball is sort of moving horizontally. And if we go back to our original diagram, sorry to give you vertigo here, but if you go back to this, you can see that at the maximum height, um, the the motion of the ball is all in the horizontal. It's kind of reached its maximum vertical height, so its vertical velocity has dropped to zero. So that's something that can help us solve the question. All right, but we're going to approach it the same way. We're going to break it into the vertical and the horizontal and write out what we know. So delta y, delta t, v naught y, v y, and a, delta x, delta t, and then vx. And in this case, again, like in the previous problem, there's a vertical, this velocity vector has a vertical and a horizontal component. So if I was to draw that vector over here, it would be 20 meters per second. And then I could break it up into the horizontal, this one, and the vertical components, right? And then the angle between them is, in this case, 37 degrees. But what we're going to do is we're going to break it up into the v naught y in this case, and the vx. So then, what do we know here? Well, what we're looking for is the maximum height. And what we're actually saying at the maximum, so what we know is the initial velocity starts out at 20 meters per second and its sine of 37 degrees. If you solve that triangle that we just drew. And this number works out to 12.36 meters per second. And the acceleration, so I'm actually making this positive. I haven't specifically assigned the convention yet, but if my acceleration is down, I'm actually going to make down positive. Down negative and up positive. So my initial vertical, which is this orange vector, which is pointed up, is positive. So that 20 sine 37 is positive. Acceleration in this case is down, so it's going to be negative 9.8 meters per second squared. And the way we just described it, the final velocity, even though this football rises and falls, we can just treat the final velocity as at any point we want. And if we want to treat it at this maximum height, we know that the final velocity works out to zero. So those are the three things I know. And the thing that I want is this, the vertical height, right? The vertical distance. And so my time is my don't know, don't care. And in fact, I don't even care what's going on in the horizontal. All this is just unnecessary for this part of the problem. And we're really only solving part A right now. So in order to do that, we just have to, with time as my don't know, don't care, I've got my equation I'm going to use is v squared equals v naught squared plus 2a delta x, or delta y, I should say. And then we're solving for delta y, so I'm just going to rearrange this. Delta y equals v squared minus v naught squared over 2a. And then plugging in the variables. V squared is 0 minus, and then we have 12.036 squared divided by 2 times negative 9.8. Sometimes when you forget about the signs, you just kind of fudge them. Like you may have done this and ended up with a negative and just been like, that doesn't make sense. I'm just going to ignore it. But the signs really should make sense. They should work out. If you look at what I have here, I end up with negative on the top and the numerator and the denominator. So they cancel out and my delta y is positive, which makes sense because it's rising, right? And when we do that math, we get delta y equals 7.39 meters positive. So that means up. So that's the answer to part A. 7.39 meters is the highest point in the arc of this football. And then the next question is asking how far away is it when it hits the ground? So now we're dealing with a situation where the ball is rising and then falling. So we kind of have to change the information we're using. And so we can't just, so for example, in the last problem, I said Vy equals 0 because I was dealing with the maximum height, right? This was for maximum height. So now I'm not dealing with the maximum height. I'm dealing with, I want to know what's going on with the football when it's sort of down here now. The football is going to end up down here, and I want to know what is the x distance, right? So we're looking for this distance here, delta x. So there's a couple of ways you can do this. We know that from our discussion of when something goes up and it comes back down, we know that it's symmetrical, meaning the time it takes to rise to the maximum height is going to be the same time as it takes to fall down from the maximum height. So what we could do is find out how far it is at this point and then just double it, because that would work. Or the other thing to think about is when the football lands over here, its vertical displacement will be 0 because it's risen and fallen back to the same height. So I think that's the way I'll solve this problem. So this is part B, vertical and horizontal, delta y, delta t, v naught y, vy, and a, delta x, delta t, and vx. Okay, so I'm going to say delta y, the vertical displacement is 0 because it rises and falls to the same height. This hasn't changed. It's the same number as before. I'm just going to put it in 12.036 meters per second. I don't know what the Vy equals, but I do know that A is negative 9.8 meters per second squared. Over here, the horizontal displacement, that's what I want. And my Vx, I can easily solve by doing the 20 cosine of 37. And that, when you do the math, works out to 15.9727, around that. So let's see. So we have my Vy as my don't know, don't care. I'm solving for time. Same, you see there's a kind of a pattern here. It has a similar, a lot of them have sort of this format. We'll put that number in here, and then we'll use what we have to solve for the delta x. Okay, so then putting this all in mathematically, we end up with, we're going to use this equation, delta y equals VO delta t, VOY delta t, plus 1/2 AT squared. When I plug this in now, the delta y is 0, right? And then this becomes 12.036 t minus 4.9 t squared. So this fact that this is 0, the fact that the delta y is 0 kind of makes this easier to solve. We don't have to go to the quadratic equation. We can factor out a delta t, in fact. There's a lot of ways you can do this. 0 equals delta t times, and then we can say this is 12.036 minus 4.9 delta t. And so if you solve this, you see that there's two solutions. Delta t equals 0, which makes sense because it's at this height, it has a 0 displacement at the very beginning. But delta t also equals, if you solve now this equation, you solve that and you end up with delta t equals 12.036 divided by 4.9. Right? It actually works out to negative 12.036 divided by negative, but that ends up canceling out. So the time we calculate in this example will be 2.45 seconds. Okay, and then putting that in here, 2.45 seconds, and then using the equation delta x equals Vx delta t. This equals 15.27 times 2.45, When we solve it, we get delta x equals 39.2 meters, which is the answer. And so that is how far the football is horizontally from where it was kicked. Okay, and then question C, hopefully it didn't trick you. It's supposed to be a trick question. It says, well, what's the acceleration at the maximum height? A lot of things change this trajectory, but the acceleration does not, right? The acceleration is 9.8 meters per second squared down, as it always is. Okay, that doesn't change. And so that's just supposed to be a little trick to make sure you're paying attention and remembering all those principles.